Hello people, how are you doing?
Hello, fine.
Okay. I see that everyone who asked questions are here, so we can start. But first I would like to ask you to ask question one more time so I can understand exactly what was not clear. And if you're ready, you can also present something.
I had a problem with the definition of area 3, which is I had some problems related to the number of Macs I found on area 5. The equation to describe the changing Mach number due to the changing temperature gave me an NaN value in Matlab. I think because it's outside the values expected that I put in the function, which means it's either negative, too big, much bigger than 1, or imaginary,
Yeah.
I think. So I changed this area because it depends on the Mach number. If the Mach number in this region 4 is too big, I think there is a problem with this equation. So I changed this area, but the relation between these two areas shouldn't change.
Yeah.
Or the properties in the inlet of area 3 would be different. So I have to calculate the properties here too. So what I did was the area changes along here, but is the same in this point. I don't know if that's okay, but since it's inviscid, doesn't really
Exactly.
the changing area here
Exactly.
shrinks the area in the end. So I hope that is not a problem. And in doing so, I had a question about what would be the optimal area here, since I'm free to choose any. And I was thinking about the purpose of the ramjet, which is to produce thrust. So I was thinking if I should find a value for this area that maximizes the thrust, or if I can use freely, since there wasn't any topic in work 1 telling us to carefully optimize this area for some parameter. So what I was thinking about was calculating the momentum generated by calculating by mass conservation. We could tell how much mass is entering here, since making this area smaller is what increases the Mach number in the outlet. So, but it decreases the amount of mass flow. I was thinking if I should make a function and optimize it relating the inlet area or the mass flow and the Mach number in the outlet.
Okay. So answering one by one your questions. First of all, of course, we are not working with the thrust of the engine, right? We are not studying aeronautic or aerospace propulsion here. We're just studying gas dynamics. And the question of thrust calculation is not the topic of this course. So you do not need to optimize the thrust or even calculate the thrust of this device because it was not asked, right? As for the question of the optimal exit of the diffuser, size of the exit of the diffuser is the following. Probably, oh, you already not sharing. Probably would be better if I share my screen. Yeah, please.
Could I just show something, just to show what happened in Matlab? So I chose this area, and the Mach number on the outlet was a bit bigger than the Mach number on the outlet. Sincerely, I was a bit disappointed by the Mach number being just 0.15 bigger than the Mach number in the inlet. And I was just checking some values. Firstly, the value that doesn't work, if I put 0.6 with it, which is the one that has both arcs tangent and the same radius, I think, approximately that, I find a value that for M5 that doesn't really work. M5 gives me net, which is not good. If I decrease it further, for example, if I put it on 0.2, which means the decrease in Mach number due to the diffuser on the area 4 is bigger, I get a much bigger value on the outlet. Instead of 2.15, I'm getting 3.78. But this area is much smaller, which means the inlet area is also much smaller, so the flow is
Yeah,
much less.
that's it.
And I was
Okay,
doing
let's
this
go step
optimization
by step
and thinking about how.
in your questions. But to explain, I need to show my screen to show the schematic.
All right.
I actually have two schematic here. One is the schematic of the diffuser, and the other one is the schematic of the rest of that nozzle and heat addition part. Okay, this is the diffuser part. Once we have this geometry defined, right, it's a bit different from what you showed, but the idea is similar. That the flow enters in the with the supersonic velocity from infinite uh, distance, right, with the known Mach number. So you cannot change the mass flow rate of air just constraining here, because when your diffuser is working optimally, these three shock waves happen. This upper line here, which I draw, is the streamline that enters inside the diffuser. So the area of the entrance is constant, and the Mach number is constant, the density as well. Uh, so here we cannot influence on the mass flow rate that enters inside the structure. When you are changing this size here, let's say the critical size inside the diffuser, in my case is 35.16, you are starting to constrain the subsonic part of the flow. What happens then when you constrain it too much? Your flow becomes supersonic, right, and starts to be supersonic in this region. Theoretically can be supersonic in this region. I say theoretically because what happens in real, when you constrain too much, the growing boundary layer will block the flow and will push outside. Pressure created in these conditions will make stronger, much stronger, our normal shock wave. And because of this strong shock wave, flow practically will stop after the normal shock wave. In this case, all the flow will break, shock waves go outside, shock waves will be destroyed, and no flow will happen. It's so-called thermal blocking of the diffuser. When the inlet part of the diffuser is too much constrained, so it cannot sustain that value you would like to, that value of the mass flow rate that you would like to push through the diffuser because of very small throat, it cannot push, and it creates a lot of resistance inside this zone of subsonic flow, and flow stops. So when you can of course set inside your computational model, inside the program, any value of this area, right? But it will not be possible to realize in the real structure. And when you will try to simulate inside work 2, it will not be possible to simulate. This is why I say that this area here is similar to the area through which flow goes near the normal shock wave. So basically this area is similar to this area right here. It can be a bit smaller, can be a bit bigger. The variation allows us to adjust position of shock waves, right? To have these shock waves meeting at the point of the upper edge, upper wall of the diffuser. And when you have this subsonic flow after the normal shock wave, as I told you last time, flow can be calculated analytically as entropic flow because we don't have shock waves anymore. We neglect presence of the boundary layer. We neglect heat exchange with the wall. and we assume that flow is isentropic. For us, it means that flow can transform to any shape, right? To any cross-section we want. What happens when we constrain more here, you understood, I hope, that we'll just or pass the flow. If it's open too much, flow can become supersonic, or can stay again subsonic. Uh, how to understand if flow will be supersonic or subsonic? I think you read a chapter of nozzles, diffusers, and wind tunnels, and you will understand in which cases flow cannot accelerate more, even from Mach 1 to divergent cross-section, cannot accelerate anymore and will stay subsonic. This is also possible. Answering simply to this question, we just need to have a big pressure enough inside the combustion chamber. Let's call this region with heat addition a combustion chamber. When the pressure is big enough with respect to ambient pressure, we have a pressure difference that decelerates the flow. So subsonic flow or flow with Mach 1 in the smallest cross section will not be capable to accelerate anymore because there is a back pressure that decelerates this flow. So flow reduces the velocity, Mach number, right? And due to the heat addition, it's accelerating a bit, but not so much. In this case, this back pressure is controlled by two factors. Factor one is the level of heat addition, because it allows us to increase the specific volume of the flow. And the second factor is the throat. Smaller is the throat, bigger will be possible pressure inside the combustion chamber. Bigger is the throat, smaller is the pressure. Smaller throat, bigger pressure. Okay, I think it's quite clear that more you constrain inside this smallest cross section with Mach 1, more will be a pressure inside the combustion chamber. Same time, you have to look backwards, right, in the direction against the flow and see if this big pressure inside the combustion chamber allows us still to have flow inside our diffuser. Because flow is subsonic in this region, it means that increasing pressure inside combustion chamber by constraining in the throat, you same time increase the pressure everywhere in this section, right, in the subsonic part of the nozzle, including the subsonic part of the diffuser, right? So when you have too small throat, right, the mass flow rate is limited, and this limited mass flow rate creates big back pressure here. This big pressure comes to the zone of the shock wave until this region here, and it makes our shock wave stronger. To avoid this process of influence of the throat inside the nozzle to the last shock wave, we are providing our calculation. We first calculate a diffuser. We calculate what are the flow properties inside the diffuser. And with these flow properties, we are calculating using Mach area relation flow deceleration here, and the pressure here is the consequence of the diffuser calculation. And further, after heat addition, we calculate the nozzle. So the nozzle is a consequence from results of the diffuser design. Right, so we do diffuser design, heat addition, and then the nozzle, all in line. So we have all parameters in a sort of the system. A system, it's a step-by-step calculation, but you understand that parameters of the throat, size of the throat is strictly related to the shock waves you calculated before. So we're closing our system in this way, calculating from left, from supersonic to right, exit of the nozzle, and in such a way we have a balance in all the flow properties that allow us to have this flow structure as we calculated. And one aspect that you just asked about the constraining here the inlet of the combustion chamber or exit of the diffuser, you can do it, but physically you can constrain until you reach Mach 1 in this section. If you decrease more than your Mach 1, of course, you cannot receive any solution because you will have no solution of area-Mach number relation. Theoretically, by area-Mach number relation, you never can obtain area smaller than the throat area, which corresponds to Mach 1. So this is why when you're trying to reduce more, right, you obtain not a number solution. This happens in several cases, right? When you constrain too much, when you add so much heat that this structure cannot sustain. For example, you add the heat that would accelerate the flow to Mach 1 and further, and bigger values. And since physically it's not possible to accelerate more than Mach 1 in a constant area duct, and the model predicts that it's not possible. In this case, you receive or complex number or not a number. I think it's something like or division by 0, but probably it's a square root of negative value somewhere in the area-Mach number relation, or the following equations that follow from the heat addition equation system. Somewhere there you have a negative square root. I hope this was the answer. It was more or less clear that your doubt was clarified. Please let me know if it's okay or you need another explanation.
Yes, I think it cleared a lot. Basically, there are many model limitations. I didn't really talk about that, but when I decrease the value of the area in section 3 to increase the
Can be
value of the
7.
Mach number in section 7 here it would be, yeah. I didn't really talk about it, but the throat area of the nozzle decreased a lot, really, like 1/10 of the outside diameter, which
Exactly. Do
could
not forget that
make some
your all
problems like the
parts
shockwave on
of your
region 3 in
calculation,
this
they are
case.
compatible with each other. They must be compatible because we physically are having, since the beginning of calculation, we physically have this mass flow rate. It's not possible to pass different mass flow rate that you have here. Air is coming inside your system, so it cannot be pushed outside by limiting this size here. Okay, that's the thing. It's not the same as you had in aerodynamics with the subsonic flow when flow goes smoothly around the body, right? In this case of supersonic flow, probably you have noticed that the streamlines, they are quite straight, right? And they do not start to rotate until they meet the shock wave or the obstacle. In our case, shock wave and obstacle is the same point here, and it starts with the start of the body. So flow came here, and at this moment it understands that there is a physical body, so there is no space to rotate, to turn around, to change any flow properties. It just enters, right? Just enters inside the system, and then it flows inside. So adjusting this throat inside diffuser, not possible to do basically anything. You just can change a little flow velocity and Mach number in this zone, in this region here, but you cannot do much with this parameter here. Okay, I hope it's clear. Please ask other question. We have to calculate the drag by itself. Right, the wave drag in this case is even if you open the Anderson book, it doesn't say much about the wave drag. Actually, what's the wave drag? It's the drag once flow becomes compressible, right? When the diffuser must sustain the drag when the flow, when this structure accelerates from subsonic to supersonic velocity. In our case, we already assume that this acceleration happened and we are flying with a constant but supersonic velocity. So in our case, the wave drag is the drag caused by the presence of the number of the shock waves in our structure. And this question was explained in the book. Here briefly I will repeat the main idea how it can be calculated. Again, this is my diffuser. And this diffuser we split into sections. So we have infinite section. On the infinite section, we have this part of external body. We will neglect the size of this external part, so it's not a question to calculate. Or the main goal of calculation of the drag on the diffuser is drag on this central body, which is composed by three sections. Section 1 after the first shock wave, section 2 after the second shock wave, and section 3 is after the normal shock wave. Also, there is a small piece here, which is 2268 is the pressure close to the combustion chamber pressure, and I will separate this in another part contribution. So it's quite simple, as Anderson states, that we know by calculation of the flow properties pressure on each section inside section 1, section 2, and section 3 by our analytical calculation. And since the Reynolds number in this task is very, very big, that means that viscous forces like friction, right, is negligibly small with respect to the pressure forces. This result is studied quite widely, and you can find it in the Anderson book, in the part of when he compares. I think it's the chapter 1 introduction to aerodynamics, when he compares pressure and viscous forces for this case of the diffuser. It's one of the first examples. So taking now this idea that drag is only composed by the pressure forces, it's quite simple to calculate this drag. We have to split drag into three components. Drag total would be drag in section 1 plus drag in section 2 plus drag in section 3. So this is drag 1, drag on this surface, drag on this surface, okay? And can be added also this small one inside the chamber, okay? This each of these drags can be calculated as a product of the area by the pressure. In this case, the area you take is the projection area on the direction you need to calculate the drag. In this case, this is the projection area, for example, area 1, right? Is not the total area of this line, not the total size of this line, but just a projection, because we split our force into two forces. One will be horizontal, which is drag, and the other one will be vertical, which is the lift. Since our body is symmetrical, we will have two forces of the lift in equal size but opposite direction. So the resultant lift will be equal to 0, and we have just a drag. In this case, drag 1 will be area 1 multiplied by pressure 1, area 2 pressure 2, area 3 pressure 3, and on the combustion chamber it will be very similar. I just need to take this open area here, so this size here I will call it AC, multiplied by the pressure inside the combustion chamber. And this is that simple. You can calculate the drag on the diffuser, taking corresponding values of the area. A1, this is my A2. Okay, this small one is A3. I did not separate. Now I can. From this point to this point, very, very small one. Okay, for the reference. And this area on which combustion chamber pressure is acting, this pressure here you take from the calculation here after the heat addition. So it's basically this area projection. When you project this area, is this value, and then it goes here. So this is the wall that creates that drag. This is the wall right here. And the projection is always known, right? It's the value of the exit cross section from the diffuser, or very close to the value of the exit cross section of the diffuser. I say close or approximate because in the work one you do not need to calculate exactly, like, you know, with the perfect precision all these forces. You need just to understand the idea. For me, it's important that you get the idea. Sorry, this plus is here. And you calculate approximately all these values. You don't need to be precisely. When you have simulation, you do it precisely because, as you know, ANSYS allows us to do this calculation in like automatic way, and to calculate the total drag or drag coefficient inside the program. Here in work one, you just need a value, more or less reference value, that will allow you in future to validate your numerical simulation. You will see if the force you found and force coefficient you found is similar to the force and force coefficients calculated analytically. And force coefficient, CD, you know how to calculate, is the drag divided by Q infinite S. Area, and this area, characteristic area, is this cross-sectional area, maximum cross-sectional area of the diffuser. Something similar you will find in the Anderson book in one of the examples. I think it's the application of hypersonic flow, and Anderson is trying to show how in a simple way calculate the drag coefficient on a conical body for supersonic velocity. It's somewhere there. I hope you already saw this example. If not, take a look and you will find the calculation of the drag coefficient on a conical body inside supersonic flow. So that simple way, this is the simple way, but at the same time, this simple way is quite accurate, because only pressure forces we have and viscous forces we neglect. They are 10, 100 times smaller than the pressure forces, so precision of our method is quite good. When I say good, you know, in gas dynamics, I mean the error is in order of 5%, precision 95% or less.
I calculated the same way, the drag on areas 1 and 2, following the book's example, but I didn't really calculate on section 3 because in arc, the component of the pressure wouldn't really be normal. So we are actually approximating the arc by a triangle in this case, by multiplying by the example, or because I was thinking I would have to use some kind of integral or something like that to calculate it, because the component normal to the pressure would be normal to the surface.
Okay, so we have this P3A3 problem, right? I can tell you the following: that P3 would be very close to P4, and you will see that P5 is also somewhere there. When you are having, since Mach number is more or less in the same level, it's not a very high supersonic Mach number. in this case, yes, pressure is acting always perpendicularly to the surface, but in this case, you do not need to find the integral because this projection is taking in account inclination of the body, and it's not important how this angle changes along the axis. This projection already takes into account this inclination or change of this inclination, and we assume that pressure is constant in each point on subsonic section, right? So we assume that from this point here until this upper point here, we have same value of pressure. When the pressure is constant, it's outside of the integral, and inside the integral only remains the calculation by the area. So it's basically the area. Okay, so we take the value of area as we know, right? It's already integral, and we use it inside calculation. So our integral becomes just a product. That's it. That's simple. It's because
Is the
variation of
consideration
Mach
of
number is
constant
very small
pressure
inside the
because
region.
of the limitations of the
Oh,
model,
sorry, it's not
or
visible for
is
you.
it
Variation
because
of Mach
in
number is
the
very small in the region at the exit of the diffuser. So after the normal shock wave and near this region, Mach number is practically constant. It means that pressure does not change, or variation of pressure is negligibly small. We can just assume constant value.
I see. I was having some trouble with that because I was kind of confused about the definition for
Yeah.
compressible flow and the changes in pressure, since I found the Mach number bigger than 0.3, so the flow there would be compressible. But
Yeah.
since the Mach
As I
number
said,
doesn't
you
change
this
along the
estimation you
section,
make
there
is
wouldn't really
mostly
be a
for
change
the
in pressure.
validation. You need approximate value. You don't need exact value until you know the last decimal point.
Oh, well,
Not much, not much. Take something average.
in my
Okay, you
case, the
can
Mach
use
number
the.
changes
You remember
along the
probably
section since the
theorem
area
of the
changes, though
average
not by much.
that allows us to substitute variation of any parameter inside integral by its average value.
Yes.
If you don't remember exactly, just look in the book theorem of average, and in gas dynamics is used a lot. It says to us the following. I will just a moment. I will draw you something of similar, that the integral of some parameter uh, along the area, which we use a lot inside calculation, can be substituted by the value of this area multiplied by p average of this average parameter. Okay, and the average parameter can be always found mathematically. This is,
So
yeah. So this is
So
your,
I
for
just need to find
example,
the
variation of
average
pressure, right,
area,
from
average
zero
vertical
from the
area
axis
to
until
calculate the pressure.
the
I
end,
just find the average
until
pressure.
the wall. Okay, and so this is P. And this integral by the areas will be this area, right? You know that integral is the area once you plot it in this way. And in your case, when you find the average value, it's not exactly the average between minimum and maximum, right? It's according to the theorem of average, it will be found as a constant P. Okay, this is P variation of x, and this constant P, that the area found by integral would be same, but just rectangle, right? So this P multiplied by area will give us the same area as we would have inside the integral. I hope you remember this theorem of the average. If not, please take a look in the mathematical book and will be more clear. Actually, yeah.
Yes.
Mm -hmm. Okay. Also take a look, and when
Yeah,
you go to
I'll
work
have to
to,
put another section for this
there is
calculation. It's not
in the
exactly
report
easy.
area average values. The area average values is actually same thing as I show you here is the ANSYS is calculating this average and gives you as the output when in the report you generate some area average, for example, pressure or area average velocity or something like this. Any area average parameter calculated in Fluent is obtained by the same concept, right, of the average theorem of the average value. It's quite useful concept. Allows us to substitute integral by just product.
Professor, eu tenho na parte 2, tópico 4, que a gente tem que fazer comparar, né, as propriedades de um bocal cônico e um em formato de bell-shaped, né? Assim, acho que você até comentou na aula passada como fazer as coisas. Acho que você comentou, você explicou.
Exatamente.
Mas, professor, eu entendi que a gente tem que usar a relação das áreas para que a gente consiga achar os Machs relativos a cada variação de área, né? Em cada seção. Só que, professor, eu não estou conseguindo fazer isso no código. Será que você poderia dar um norte em alguma... Tipo, eu não tô conseguindo, tá dando tudo errado.
Perfect. Do not forget that we also have monitors that did this and had SS at the end of the course, and especially Jan, who is the last monitor appeared in the group. He is a monitor for several semesters already, not the first time, so he's working with this constantly and has a lot of experience in gas dynamics. So I hope he could help. But if Aleph could help, it would be also great.
Só para dar um norte aí, Aleph, porque, sério,
batendo
nisso já tem um tempo, vai.
So, here is the code I made. So, there are the parameters at the inlet. They are necessary. I made a function. I didn't really know how to export the points from the CAD model. So I just made a function of the area.
Yeah, it's three arcs, as can be seen.
Justo. Pode ser só no reto. Esse daí é do reto, né? Do cônico,
no, that's the bell-shaped.
Bell-shaped, tá. Tudo bem. Então,
three arcs defined by some points I took from the CAD. So then I have to use the Area-Mach number relation to find the Mach number at each X point I defined in each area. So I know that the flow is subsonic before the float, which means that for X less than the float value, I use the F0 to find it. So I define the Mach number equation this way, and I use F0 with this equation along the medium point I expect. So I expect the value of the flow to be somewhere between the Mach number at the inlet and 1, because it should be 1 at the float. So I just took the average value for around where I should take it before the float, and I took it in the float too. In the second region after the float, I expect a value between the Mach number in the exit of the float and in the exit of the nozzle and the inlet of the nozzle. So I took the average again, and I was having problems because I was having the same solution on both sides, and then I found that I should solve around the point I expect the value to be, and then it solved my problem. Then I calculated the same way, but with vector operations, using the Mach number I found as a function of x to find
As temperaturas, pressão, tá.
Yes, and then
eu tô aí nesse... Aí, botou tudo, né? É esse negócio aí mesmo, é isso que você tá mostrando aí. Então, Pera aí, esse primeiro if é para um valor de x...
Before the float, I do the function to solve the value of the nonlinear equation around a value of the Mach in the inlet and Mach in the throat.
Tá.
And here, I probably should put between 1 and Mach in the outlet.
É que seria o da área 6 ali, né?
Yes, after the throat. It's already the Mach that should be in here, so should make it a little better. And then I just plot the results, and I find the bell and this the comparison one. So the conical one, I have the ratios of pressures, temperatures, and here we see, I think it makes sense. We see the value, the value of the state quantities related to the internal pressure decreasing and the values of the numbers related to the velocity increasing. So, which for me means we are converting internal energy into kinetic energy, which I think is the
Yeah, that's good. They're
reason
quite
for
good.
the
But don't forget that it's better
bell
always
nozzle
to
and the
plot
conical nozzle. And the same thing
pressure
on the
ratio
conical,
in the
but a
logarithmic
smoother
coordinate
shape. I think the
because
graphics
there is
make
a
sense.
variation between very big values and very small values at the exit of the nozzle. And also do not present in this aspect ratio because they look very long size. Make something like golden ratio like we usually do or square.
Okay.
They look much better. And I've already commented this several times
I'll try to make presentation better.
when I
Should I
explain
put a
how it
grid
must
too?
be done. Presentation of pressure ratio in logarithmic coordinates makes much better visualization. You can see same time big values and small values on the same plot. It becomes much more representative than just a linear scale.
Ok.
Valeu, Aleph. Eu acho que eu entendi. Eu vou tentar pegar essa lógica que você fez e seguir aqui. Valeu.
Following the train, since I'm already here, just about how I did the optimization for the values of theta, I found the same values as Gustavo. I think he showed his figure. So I did the optimization for theta and beta. The beta is a bit discontinuous, but the thing I found here was that this region I have no plot is kind of a region where it doesn't make sense to plot. I'd like to know if it's correct. My reasoning here for this region that doesn't really exist in the plot is how I found the values. So to the optimization first, I calculated everything as a function of beta. So I put an interval of beta, calculated theta, and the properties after that, the efficiency, and did also that for the first region and second region and plotted everything as a function of theta 1 and theta 2. But I was having some problems with convergence, and I found that it was because the model, I was using the model wrongly. So if the Mach after the first shock wave is less than 1, there shouldn't be a second shock wave. So I just put that if the Mach is less than 1 after the shock wave, I'm not interested. And the same thing after the second shockwave, because if so, there wouldn't be third shockwaves. So I did it again, and after the third shockwave, we should have the flow we expected. So these NaN values are what is limiting my plot as a function of theta and beta, and they are related to angles that don't generate all the shockwaves. So I don't know, because I use a different method from the suggested, I think, since I just plotted the efficiency in terms of theta 1 and theta 2. I'm wondering if there's some
Yeah,
problem
that's a great method
not
that
really
allows to save lots of
accounting by the
computational time,
non-generations
right?
of the
Just
first and
calculating
second
the
shockwaves if
half.
the angles
Of
of
course, it's
theta 1
not
and
the
theta 2
super efficient
outside this
method
region.
as, for example, the gradient method when you just need, for example, like 5 to 10 iterations in total, right? You calculate lots of points, generating these nice graphics. But it's a great thing, and I think it's a very nice program to when you first time working with this concept to optimize things. You can see clearly where there is a maximum of this function that corresponds to the optimal combination of the angles. right? Which is very very nice from the visual point of view. What else? Nice. Congratulations. Just one comment here that I saw the program you calculate separately, shockwave 1, shockwave 2, and shockwave 3. If you look closely to the general concept of shockwaves, you can, I'm not suggesting, but in future, if you're interested to work further on this, modify this program because all the shockwaves calculated in the absolutely same way, even the normal shockwave is calculated in the same way as the oblique shockwave. So you can make a loop calculating shockwave one after the other, right? And you just need one piece of code to calculate just one shockwave, and then you repeat many times as you need number of shockwaves. It allows to optimize not just a two oblique shockwave diffuser, but to optimize many shockwave diffuser, right? The multiple shockwave. Yeah.
Makes sense.
Yeah. So it can be not just two parameter optimization, but many parameter optimization. And this opens new possibilities. But this is not the goal of current work, so please do not make it because not time enough. Just work if you like on your free time, and then let's see. It can be a nice result at the end. You will see how to go from this type of calculation to Prandtl-Meyer flow, reverse Prandtl-Meyer flow calculation, which is much simpler, but gives absolutely same result as the oblique shockwave theory. Congratulations on this program, it works nice.
Thank you. So I think I had, the last question was the one I posted on Aprender, was about the isentropic. I had, in kind of something I had discussed with the monitor after, which is the equation used for the heat addition for the region 5. Let's see, where is it? 3, 4, and 5 here. So in the class, it was shown that the isentropic temperature on 5 would be the isentropic temperature on 4 plus the temperature increase.
Yeah, which is much simpler in this case.
On his semester, on his code, he used another relation. He didn't use the isentropic values, but he used the equations.
For my opinion, more correct would be to work with the stagnation temperature, because so once we add the heat inside each, let's say, fluid element, we are adding to the global energy. When we are adding to the temperature, we are not taking into account acceleration of the flow with expansion. And in this case, we lose a bit of accuracy. As you saw, probably T05 and T5 would be very similar. Difference between them may be 1-2%, not so much. They are really close one to another. And in this case, you do not lose too much. You do not lose too much. But from the logical point of view, from the modeling point of view, it's more reasonable to add to the stagnation temperature as the global energy, right, change than just to add to the static temperature, because static temperature changes due to the velocity, and the global temperature, I mean the stagnation temperature, is not changing, it's just changing due to the heat addition, right? And the static temperature is changing not just because of this, but also because of flow acceleration and deceleration.
Yes, the most of the reasons I was having problems with this region was because of the value of M5 not being real, so I thought maybe it was this relation. And the relation is kind of involved because the value not being real is because the solution for the equation is not real in the case. But I was really having some problems with the relation between an isotropic process.
I understand completely, because for each input Mach number, there is a limiting value of heat addition that this flow can sustain and to have the flow properties, because some flows, they cannot be heated until some values, right? If the flow is too fast moving inside the cylindrical pipe, it physically cannot be heated more and continue moving. It will start to stop, as I already told you at the beginning of the class about the thermal. Yes, there is a way. There is a way. You just analyze the. Okay, you solve this equation of
Is there a way to calculate how much
stagnation
it can
temperature ratio
accelerate to make this program
and
give me values?
add Mach 1, Mach equal to 1 after heat addition? You put two parameters. There is nothing to solve. You just put parameter of Mach number before heat addition to this equation and after the heat addition on the right part of the equation. So on the left part of the equation, you will see a limiting the maximum possible temperature ratio that can be realized in this flow. I saw that sometimes students have this kind of limit. Every semester I say that if you reach the limit of flow heating, just decrease delta T
So
until the
it would
level
just be
that
a change in
flow is
this
still
function, this
subsonic,
giant
right? And
function.
still not just subsonic, but has some reasonable value of Mach number. So no new questions. Have a nice end of the day, and we meet next time when there are questions. Thank you for coming today.